Today in this lesson, we will be studying what is K-means clustering and most importantly, how we use elbow method to determine the optimal number of clusters for our data. Let us start with the basics by understanding what are these clusters. To better understand this, consider a simple example of human height. Imagine we plot a data set of individuals based only on their height along a single line. The data points are simply scattered across the axis, but we can visually see some groups forming there. People with similar height naturally appear close together. As shown in the image, we can visually identify three distinct groups: a short group, blue one, a medium group, the green one, and a tall group, the orange one. These natural distinct groupings are what we call the clusters. This is the initial intuitive idea that the K-means clustering aims to automate. Now that we know what a cluster is, let us look at the K-means algorithm itself and understand how it works. So the very first step is to select the number of clusters, that is K. This K represents how many groups we want to divide our data into. In our previous height example, the K was 3, short, medium and tall. However, in real world scenarios, we don't always know the ideal value of K. This leads us to the question, how do we choose the optimal value of K? Well, there is a technique called elbow method that we will see later on in this lesson. Moving on to the step 2, initialization of centroids. Once we have selected our value of K, which is 3 in our example, the algorithm proceeds to randomly select K distinct data points from the dataset. These selected points are called initial centroids. A centroid is essentially a temporary point representing the center of a potential cluster. As you can see in the diagram, 3 points have been randomly selected and colored blue, green and orange to serve as our initial cluster centers. These starting points may be random, but the algorithm will iteratively refine them until the optimal cluster groups are formed. Now we arrive at the step 3, the assignment phase. In this step, the algorithm calculates the distance of every single data point in the entire data set from each of the k initial centroids. Once all the distances are calculated, every data point is assigned to its nearest centroid. This is the step that forms the initial k clusters based on the proximity to the randomly selected starting centers. Let's visualize how exactly the step 3 works by looking at few examples. Consider this point 1 for which the algorithm measures its distance to the blue, green and orange centroids. Clearly, this point is closest to the blue centroid, so it gets assigned to the blue centroid. We repeat the same process for the point 2. Again, we calculate its distance to all the three centers, and this point is again also close to the blue centroid, so it gets assigned to it. Following the assignment rule in similar manner, we will assign the next points to their respective closest centroids. The algorithm has successfully partitioned all the data points into three initial clusters based on which of the centroids they were closest to. However, the current centroids were just our random starting points. This leads us to the critical step, step 4, updating the centroids. For each of the clusters, the algorithm calculates the mean of all the data points belonging to it. Then the existing centroid is moved to the newly calculated mean position. As you can see in the diagram, the blue, green and orange centers have been shifted to their actual mathematical centers of their respective groups. After the centroids move, the entire process must repeat. We go back to the step 3 where all the points are reassigned to their nearest new centroids. The centroids will keep shifting until they no longer move significantly and we will get our final clusters. We can assess the quality of clustering by adding up the variation within each cluster. When points in a cluster are closer to their centroid, the variance or spread is low. When points are scattered far apart, the variance is high. Our goal here is to minimize this total variation. Since the starting centroids are chosen randomly, the final result can vary significantly for each attempt. To get the most optimal clustering, k-means usually runs multiple times, each time starting with the different initial centroids. For each attempt, we calculate the total variation within the clusters. The attempt that brings the least variation within a cluster is selected. Here we can see the third attempt is the one with the most optimal clustering and hence is the final result that we have achieved. We previously saw that selecting the initial number of clusters k is the first step in k-means algorithm. But if we don't know the natural groupings in the data, how do we figure out the optimal value for k? The answer is simple. We just try out different values for k and the one which gives us the best result is selected. Let's start with the extreme case that is k equals 1. The entire data set is treated as a one single cluster. This is the worst case as you can see in the diagram. The variation is very high here. Next we run k-means for k equals 2. The total variation within each cluster here is significantly lower than when k was 1. We continue this process for k equals 3. This divides the data into 3 clusters and the data points are even closer to their centroids. As a result, the variation has reduced further as compared to when k was 2. Since the data visually seems to have 3 natural groupings, k equals 3 appears to be a good fit. But let's increment k for one more time and let's see what happens when k equals 4. When k equals 4, the data set gets divided into 4 clusters and the variation reduces further. The key insight here is adding a new cluster each time will always reduce the variation until we have 1 point per cluster, that is zero variation per cluster. This leads us to the elbow method which says run the k-means for a range of values of k, say from 1 to 10. Then for each value of k, calculate the variation within each cluster. Then plot the graph of variation on x-axis and k on y-axis. The curve will decrease sharply at first, then it will start to flatten out. The point where this sharp decrement slows down, that is the elbow point, is chosen as the optimal value for k. Notice there is a sharp drop from k equals 1 to k equals 3. However, the curve starts to flatten out at k equals 4. This point, that is k equals 4, is our elbow point. Adding up another cluster at this point will not give us that much of reduction in the variation. Thus, k equals 4 is the optimal number of clusters for this dataset.